All right, so in this video, we're going to look at the difference between mass and weight. I think up until now, there has been no difference between mass and weight. Certainly in chemistry class, these are used interchangeably. But in physics, we make a big distinction. Okay, mass is how much stuff you have. Weight is the force of gravity. So in physics land, weight, gravity, there we go. Weight is in newtons, mass is in kilograms, okay? Let's just look at that just a little more closely here. Mass is the amount of stuff you have, technically speaking, right? So it equates to protons, neutrons, electrons, plus energy, by the way, just going to say. Okay, so however many protons, neutrons, electrons, roughly, this is going to give you the amount of mass you have. It's related to moles, right? It is actually measured in kilograms, grams, and the U.S. the English unit of mass is actually a slug. Okay, now a kilogram is a unit of force or unit of mass that when you exert 1 Newton, right, it accelerates. It causes an acceleration of 1 meter per second squared. Okay, a slug is an amount of force or is an amount of mass that when you exert a pound, right? If you exert a pound, the object accelerates at 1 foot per second squared. Okay, we're not going to use slugs, but you can convert slugs directly into kilograms, right? Now here's a question: which one's bigger? I'll give you these clues, right? A meter per second squared is actually 3.281 feet per second squared. So a meter per second squared is a bigger unit of acceleration. And a pound is actually 4.45 newtons. So a pound is a much bigger force than a newton. And when it acts on a slug, it causes a much smaller acceleration than a newton does on a kilogram, right? A newton is a much smaller force than a pound, and it causes a bigger acceleration on a kilogram than a pound does on a slug. It's like, you got that? All right. It is a measure of inertia, so if you have more mass, you have more inertia. It is not zero in space, okay? You can be weightless, but you cannot be massless. Only things like beauty, truth, music, integrity, right? Those things could be zero in space because they're abstract concepts, although I would maintain for them to exist, one must think about them, and thinking is energy and energy is mass. I'm very literal that way. All right. Weight, okay, look at this, look at this. This, by the way, I won PowerPoint of the Year in 2004. Look at this animation. Weight, whoa, it comes down. You can see it's like gravity. Weight is the force of gravity acting on an object, right? Weight is measured in newtons, okay? It is measured in dynes, it's measured in pounds, okay? So if you're talking about pounds, that's weight, it's not mass, okay? If you're dying to know what this unit is, a dyne is the amount of force needed to accelerate a gram at 1 centimeter per second. Much smaller than a newton, right? A newton accelerates a whole kilogram at 1 meter per second squared. If you do not have a gravitational field, then you will not have weight. Okay, so it's zero. You can be weightless, right? If there's no gravitational field, or if, by the way, if you're accelerating in the same direction as a gravitational field, you will also feel weightless. Okay, and then the demo calculation here, right? And this is very simple. If I drop 1 kilogram, it accelerates at negative 9.81 meters per second squared, right? So my force, the force that's acting on it is 1 kilogram times 9.81 meters per second squared, right, is 9.81 newtons. Okay, so if I have 1 kilogram, its mass is 1 kilogram. Mass is 1 kilogram. It will have a mass of 1 kilogram in space. It'll have a mass of 1 kilogram on Mars, on the moon. If we move anywhere we want, we still have that many protons, neutrons, and electrons. It's going to react with the same amount of sulfuric acid and make, I can't remember, ferrous or ferric sulfate or something, right? It's going to behave, it's going to have inertia. It's going to be hard, it's going to have the same resistance to throwing it, right? On Earth, it weighs 9.81 newtons. On the moon, about 1/6 that. On Mars, I think it's like 30% of that or something like that. Its weight is all over the place. The weight depends on the gravitational field, okay? If it's orbiting the Earth and accelerating toward the center of the Earth centripetally at whatever the acceleration is, right, it would feel weightless. It would have a weight of 0 newtons. In deep space, it would have a weight of 0 newtons. Okay. Really, in the data packet, if you dig around, you'll find this formula. It's way down in field theory somewhere. So G is really a gravitational field strength. When I said G was 9.81 meters per second squared, I lied to you. It's actually, G is actually 9.81 newtons of force for every kilogram of mass. Literally, that's what it is, okay? It is a gravitational field strength. And then is there anything else? Let me hit the right arrow. Oh, no, that's it. Okay, so that is the difference. Don't confuse them. Don't use them interchangeably. Okay, if you ask me how much is, what does this weigh? Okay, I'm going to tell you in newtons what it weighs. Okay.